Okay, so let's see what we've got. So up to now, we have the following equations. So we have that the divergence of E is equal to rho over epsilon 0. That's what our friend Gauss tells us. We have that the divergence of B is equal to 0. That's the friend, no-name friend. That's what this person tells us. Then we've got Faraday's law, which is that the curl of E is minus the time rate of change of B. And finally, we have Ampere's law that tells us that the curl of B is equal to mu 0 J. Okay, and the question is this okay? Well, there are many checks that we can make on this. So unfortunately, there's a fatal inconsistency in there. So no. Why? Well, let's try to take the divergence of the curl of B. Okay. So if I number them, let's say that this is 1, 2, and then 3 and 4. So if I do this from 2, then this gives me 0. But if I do this from the fourth equation, then that gives me mu 0 div j. But we know that div j is not equal to 0 by the continuity equation. Right? So we had that the div j was equal to minus d rho dt by charge conservation. Yeah, so by continuity equation. The other equation telling us the divergence of the curl of E, that one works out because then we can just indeed use the continuity equation, and that's going to give us the right thing. But this one doesn't work out. Okay, so maybe a kind of physical way of viewing this, so by an image, is let's imagine that we have a circuit made of a current carrying wire carrying I, and then it's got 2 plates of a capacitor. And then the current coming out like this. Okay, so let me do 2 things. So let's imagine that I'm taking a certain Amperian loop around this wire here. Okay, let me integrate, let me apply Ampere's law to that little loop here. What does that tell me? So Ampere tells me that if I was to integrate over P dl B, I would get mu 0 I enclosed, which is equal to mu 0 I. If I'm taking the surface, which is the flat surface defined by this. Okay? So that's kind of working up to now, because I imagine that I've got my current, I've got a magnetic field induced by that current, and I should get a kind of result as I expect. But let's imagine now that I'm doing precisely the same loop integral, but now my surface is a kind of bubble, a kind of bottle, going in between the plates of the condenser. Okay, so for this second surface too, so mu 0 I enclosed is equal to 0 for this surface. Okay? You see, there's no current going through it. So in this case, although my path is well defined, choosing different surfaces gives me different results for the current enclosed. There's a current here because the wire is just piercing my surface. But in this case here, there's no current. So that's zero. So that's inconsistent. And this is where, you know, your insight comes in handy. The idea of Maxwell is to fix this by adding an extra term to Ampere's law. So fix. No. So this is due to Maxwell. A time-dependent E induces a magnetic field. Okay? Quite symmetrical, in fact, with what Faraday taught us. So the time-dependent E term that needs to be added turns the Ampere equation into the following. I have to say that the curl of B is equal to mu 0 J plus mu 0 epsilon 0 dE dt. Okay, and so this is the Maxwell term. Yeah. And the nomenclature here is that Maxwell introduced the so-called displacement current. Very unfortunate choice of name. Okay, so this displacement current, JD, is just epsilon 0 dE dt. And that fixes the problem that we have, because now you see, I mean, the calculation is done in the notes, but I don't really have time to show it, but we can just talk about it. So what happens when there's current coming through here? There is charge accumulating on the plates. And if I have two capacitor plates, there is an electrical field between the two. Remember, I would just do my little Gaussian pillbox here. If I've got a certain surface charge density sigma here on both ends, then there would be a discontinuity of sigma over epsilon 0 across the two boundaries here. Between the two capacitor plates, there is an electric field, which depends on the surface charge density there. But the surface charge density is increasing in time if I'm measuring it here, and my current is going this way. Therefore, there is a time-dependent electrical field between the plates. And it so happens that if you include the Maxwell term here for the displacement current in this thing, it precisely carries the same weight as the current that is carried through the wire when you consider it like here. Okay, so then it becomes consistent.